So the first example, you will see that we try to force the probability density function into this small subinterval in space. And then the second one will be the tracking of a non-smooth target. So in this specific example will be a moving uniform distribution. Okay, so here you see on the left the region avoidance example, and here the non-uniform tracking. So okay, here the moving the target is moving, and the blue line, that is the solution of the probability density function, can follow the target pretty well. Of course, the controls need to have these spikes where the target is non-smooth. While here it seems that everything is constant, but actually, as you see, the control is always acting because it has to prescribe the solution only between 0 and 0.5, but we do not prescribe the shape of the probability density function. Okay. All right. Then actually, if I have time, do I have other 2 minutes?
Yes.
Yeah, thanks.
Yeah.
So I also show you another couple of simulations. So the first one is in a multi-D domain. So we consider this two-dimensional stochastic process that models the dispersion of substances in shallow water. So this is the variance matrix sigma, and this coefficient D is given here. So of course we have the uniform ellipticity property, and then this is the drift function, okay, that has two components now. Okay, so as initial distribution, we take let's say a Gaussian, so it's a smooth delta Dirac located at 0.44. And then the target will not be moving, will not be a dynamical target this time, will be a fixed probability density function that is given. So for as a target, we take an equilibrium of stochastic Volterra model. But I mean, this is not very important. So all these properties have some physical meaning. And then, okay, and of course, well, also before I did not mention, but we also have control bounds as well. And also here I compare, so this is the initial condition, you see, the smoothed delta Dirac. And this is the target. So in this first example, the first simulation, we show what happens when the control is only time dependent, so does not depend on space. And as you can see, starting from the initial condition, it can go where the target is, but then, as in the 1D case, cannot reach the peak. Actually, it fades out quite quickly, okay? And then in the second simulation, we apply a control that depends both on time and space. Again, this is initial condition, this is the target, and this is the two components of the control, because of course the control now is also two-dimensional. And as you can see, the initial condition is shifted where the probability density function target is, and then it can follow it very well. All right. Okay, so actually I'm about to conclude, but I want to finish with a few remarks. So the first one that is actually quite interesting in our for us is that, so we started from a stochastic optimal control problem. We rephrased it in a completely deterministic way. We study and solve numerically the optimal control problem constrained to a FOKKER-PLANCK equation, forgetting about the stochastic process, okay? But then what we did was to try to take the optimal control that we find for the FOKKER-PLANCK equation, so for the control of the probability density function, and to plug the optimal control in the stochastic process, okay? And for this, I want also to show you some simulation. Please tell me if you see if you see,
No, you're seeing your Google Meet.
Okay, no, I wanted to open. Yes, let's see. I cannot find it. That's weird. Just a second. Okay, I cannot find it now, but because I really wanted to, let me stop presenting a second. And I will try. No, it's not there. Okay, so I can find it again. Okay. And now I share again with you. You can see my screen again?
No, now it's coming, now it's coming.
Yeah, okay. Okay, so now I show you what happens when we plug the optimal control that we find for the FOKKER-PLANCK equation that you can see here on the left into the stochastic process. So here what you see is 500 realization of the stochastic process. This is what it looks like a step function, right? In red. And you can see that plugging the optimal control that we find for the FOKKER-PLANCK equation into the stochastic process gets a very good tracking of the desired probability density function, also for the many realization of the stochastic process. Okay, so here you can see this for the Ornstein-Uhlenbeck process. Then we also did the same for the geometric Brownian motion. And also in this case, as you can see, the stochastic process, the realization of the stochastic process follows very well the PDF, the probability density function, as solution of the FOKKER-PLANCK equation. Similarly, for the Shirev problem, here you can see also the Ornstein-Uhlenbeck again, where the target has two peaks, and also in this case, the tracking and the stochastic process tracks very well. And also the case of a non-smooth target, okay? So in all these situations, the stochastic process behaves very well when we plug in the stochastic process the optimal control that we find for the FOKKER-PLANCK equation. All right, so now I go back to the slides. I think you see them again, and I'm really concluding now. Then another issue, since then we studied the problem on a bounded domain, it would be to consider zero flux boundary condition, which are embedded in the numerical schemes when we apply this Chan-Cooper scheme, but are not in the let's say existence of optimal controls. Then, as I said, the model predictive control scheme must be studied in order to ensure stability, and this was done in this paper by Arthur Fly and Lars Grune, which, by the way, it was mentioned in the first slide. I don't know if I said they are the main collaborators in this project. And then also, as I mentioned at the very beginning, so this combination of FOKKER-PLANCK and model predictive control approach has been applied by the EDF lab, which is the electricity company in France. Well, at least from their research and development lab, to model and control populations of large number of electric hot water tanks, which it's, let's say, something connected with the distribution of utilities over large networks of users and suppliers, as I said in the introduction. Okay, so that was all, and I really thank you for your attention, and that's it. I'm looking forward for your question.
Thank you, Roberto. Thank you very much. I think we went a bit further than I was expecting. So maybe there's a time for one or two quick questions in the audience. Maybe if anyone wants to talk and wants to maybe to type in the chat, so I will handle the word. So okay, I have one question, Roberto. So
Yes.
You're solving all this. I mean, you're solving all these problems with with stochastic problems like Ornstein and Lebesgue. But from time to time, for instance, instead of Ornstein and Lebesgue, maybe you want to use the CIR model, which has a square root y in the volatility, and that breaks your first assumption of uniform ellipticity.
Mm-hmm.
So can you any chance of extending in that region of models, or?
Well, actually, thanks a lot. That's a very nice question. Well, actually, this is something very reasonable. So in many contexts, in particular, actually, whenever we are coping with the processes that evolves in a bounded domain, we may imagine that this bounded domain is actually conserved, so it's preserved by the stochastic process, right? And this actually is often the case when the volatility matrix or the parabolic operator, which is associated, let's say the Kolmogorov operator associated with the process, becomes degenerate on the boundary of the bounded domain. So this is actually a very natural question to extend these results to a FOKKER-PLANCK equation, which is degenerate, so the diffusion coefficient, diffusion matrix degenerates along the boundary of the bounded domain. And yeah, this is something we have in mind.
All right, great. Thank you, Roberto. Any other questions before I hand over the word? I switch back to the main organizers. So okay, if not, so just thank you once again, Roberto, for this very nice talk.
Thanks a lot to you.
I think, and I'll hand it back to the other organizers, to Juan and to Mauro for the next talk.